All right, welcome everybody to Wednesday of week 15. Today we're going to be talking about more pointer stuff, but we're going to actually get into some CSci 45, which is our computer architecture class. I'm actually going to explain some concepts from that today because the only way the things I'm going to teach today are justified is once you understand a little bit of architecture and when you understand a little bit of computer architecture, not like buildings architecture. When you learn computer architecture, you learn how to write code that will run faster, even though it's the same code correctness. Like you could add up all the numbers in an array, either going across the rows or going down the columns, and numerically it's the exact same thing, right? You're adding all the numbers together. But if you add them up going across this way, it'll actually go faster than if you go down the columns. And that wouldn't make the slightest bit of sense until you've had the lecture we're going to have today. So I guess I'll start off just by explaining a little bit about something called the memory hierarchy. And hierarchy, if I'm spelling that right, is an E. Hierarchy. Nope, with an I. Okay. Had to write the first line. Memory hierarchy. Okay. So inside of a computer, how many people here have ever looked at like the specs for a CPU before? Like you've gone, to Best Buy or something, and they sell like a Core i3, an i5, an i7, an i9, or a Ryzen 3579 or whatever, or a Threadripper or something like that. Have you ever actually like looked at the specs on a CPU? I'm going to pull up the specs on my CPU here. It's a KF. And usually what people look at is this thing here, which is the clock rate. So the clock rate is, the clock inside of your computer is a piece of crystal or something like that that sends out a high voltage and a low voltage, in this case, 5.8 billion times per second. It actually varies quite a bit. If you look at my computer right now, I have down-tuned my computer. I actually run my computer at a much lower performance than it's supposed to run at, ostensibly, if you look at these numbers. My computer is currently running at 1.5, 1.8, 4.4, 1.5 gigahertz, which is quite slow for a system that could run all the way up to like 5.8. And the reason why I do that is because of heat, right? So I'm not doing anything... I'm not doing anything worthwhile with my CPU right now. I'm streaming, I'm recording, I'm on Discord, I've got a couple browser tabs open, stuff like that. Nothing really like meaningful. My CPU utilization's at 15-ish%, right? So I don't need any more power than what I need right now. But if you look at those stats, in fact, actually, it shows you right here. It shows you something called the cache size. And so here it says 36 megabytes of Intel Smart Cache, 32 megs of L2 cache, but it actually doesn't give you actually all the information that I'd be interested in. But my program here does. And so if you look at this, you can see here I've got what's called a data cache and instruction cache, which is combined called the L1 cache. We've got this thing called an L2 cache and the L3 cache. And what this is, okay, is an attempt to make RAM not suck. So RAM, we all think of RAM as being fast, right? Like if something's in RAM versus on your SSD, or Lord forbid, on a spinny disk HDD, we think of RAM as being very fast, but it's not. RAM is actually slow. And so if you have, like on my system, I've got 64 gigabytes of RAM. In the amount of time it takes for that, like if I say integer x equals 420, in the amount of time that it takes me to like read a value from RAM, I could do 100 cycles. And these are all just ballpark figures. The actual numbers depend on a lot of things actually. But what is a cycle? Remember, a clock in your computer, right now I'm running at 1.7, 2.7, 1.6. Let's just say 1.5. So 1.5 billion times per second, there's a little piece of crystal or something that sends out a high voltage and a low voltage. If you're in the high voltage, all the pieces of machinery inside of your CPU operate. When it goes low, they all stabilize. And that is called one cycle. High, low, that's one cycle. And in one cycle, you can do like one add or something like that. You can add two numbers together. Okay. So RAM, while it is fast, you could load, in the time that you're loading, you could do like 100 bits of arithmetic. You could do X is equal to Y plus Z and all this kind of stuff. Assuming that you don't have to do any loads from RAM, you could do a lot of stuff in the amount of time it takes to load from RAM. And this sucks. This is really bad, right? And if you had to do this every time you read or wrote to RAM, your machine would be 100 times slower than if you didn't have this penalty. So what people have done, what these computer engineers have done, is rather than going directly from the RAM into your CPU, what happens is that it goes into your cache. So you have something called a cache. And inside of the cache, there's actually different tiers of cache. There's L3, L2, and L1. But at the end of the day, this is going to go into your CPU, your central processing unit, into something called a register. And the register is where your variables are actually going to be doing stuff. So when you add two things, you're adding the value in this register to the value in this register and saving it into this register over here, that kind of stuff. How many registers does your CPU have? 70, 80, depends on the computer architecture. ARM32 has 16 plus a couple special use ones. x86 has only a handful of usable registers, but under the hood has actually got 70, 80, whatever the actual number, doesn't really matter. Different registers. Now, there's different tiers of cache. L3 is big and slow. L1 is small and fast. So the L1 cache we saw from my thing here is 48K and 32K, and that's 48K on a performance core, 32K on an efficiency core. So we'll just look at performance core, I guess. So each performance core has 48 kilobytes of RAM, which is not a lot, right? It's not a lot of RAM. 48K is not, that big, but that's for your program. And so anyone know how big a program actually is? Like the actual compiled, version of your code? Anyone know how big that is? Like for Cyberpunk or something like that? Like the actual executable size? Like Cyberpunk's like what, 70, 80 gigs? Let me see. Let's see, Starfield. Let's see here. Okay. So Starfield's 116 gigs. Borderlands 3 is 140 gigs. Cyberpunk's 76 gigs. Yeah. Okay. But if I were to open up the, let's see here, installed files, browse. If I were to open up the Cyberpunk directory, the red launcher setup, where is the actual executable? I don't think that's the actual executable, it's the launcher. Maybe under bin or something like that. Cyberpunk, there it is. 57 megabytes. Okay. And probably a lot of that isn't actually, program, right? There's a lot of other stuff that's in an .exe file. Now, there's a lot of stuff that are technically code that are not baked into the executable itself. These are DLLs. They kind of like socket into your executable to do things like curl, which will transfer data over the internet, things like that. So if you add all this stuff together, you're talking 300 megs maybe. But this includes things like your shaders and the error reporter and things like that don't really matter. The actual executable, let's say 57 megs. Okay. Now, your instruction cache is only 48K. But here's the thing, like 48K, like every instruction you have, let's say, is about 8 bytes. And as long as all the program you're doing is in the same loop over and over again, all of that data is going to be stuck in cache. Because what cache does, it says this. The first time that you load the value of X or something like this, it's not in cache. You're going to get what's called a cache miss. And it's going to take you 100 cycles to get this data. But then once you've loaded X from RAM into your register, there's going to be a copy of it at level 1, level 2, level 3 cache. Okay? And as long as you keep using it, you're reading it, you're writing it, you're reading it, you're writing it, it'll stay in cache. And then once you stop using it for a while, it'll first fall out of L1 cache, because L1 cache is the smallest. And then if you don't use it longer, it'll fall out of L2. L2 here is 2 megabytes. So we have 2 megabytes per core here. And then if you don't use it, you don't use it, you don't use it, it'll fall out of L3 eventually. L3 is a unified 36 megabyte cache that is shared between all the different cores. And then it'll only be found in RAM again. But let's say you don't use it for a while, it falls out of L1 cache, but then you use it again, you'll find it in L2 cache, okay? And so basically the most hotly used stuff would be found in L1, and if you haven't used X in a while, it'll eventually get dropped because you haven't used it in a while. But then you use it again, and then the system will find it in L2, and it'll bring it back. Okay, we're back, baby. We're so back. And so the faster caches are the smallest, right? So the L1 cache, you might think of this as like a 4-cycle delay. L2, just spitballing numbers, like 10 cycles. Again, all of this depends on your architecture, your clock rate, things like that. L3, maybe, I don't know, 30. I'm just making numbers up here, but the idea is just to kind of give you like a ballpark idea of what we're talking about here. And so as long as all of the values you're working with are held in L1 cache, Skyrim is, what do we got here? 34 megs for Skyrim, yeah. As long as all of the code, like the loop that you're within, you're in a for loop or something inside of Skyrim, that's probably less than a K, right? That loop you're doing stuff in, right? It's probably maybe, I don't know. I'm just making up numbers here. Well, let's say it's like 500 bytes or something like that. All of that's going to be in cache. You're not going to suffer any delay penalties. Okay. So, the bigger the cache, the more stuff you can hold. Okay. But here's another thing about caching. When you load from a array, if you have an array, let's say we've got 100 elements in the array, it goes from 0 to 99. ... Yep. When you load an element from an array, what happens is it's actually, let me color this in blue, green, blue, let's see, blue. It'll actually load all of the data around it as well, okay? Because you've gone to all that effort of getting one integer. The bandwidth isn't the problem is the delay. And so when you load this guy here, it's actually going to load everybody around it at the same time. So if you've loaded index, what was this, 2 here, and then if you do something like cout the left arrow array square bracket 2, that could suffer a 100-cycle delay because it's not in cache. So it's got to load all that data, and all of that data gets saved into cache. Okay. But then you also cout array square bracket 3. This will probably be in cache, right? Because you just loaded the guy next to it. Do you guys are you guys having trouble viewing the stream? Let's see, stream settings, 15 frames a second, 1080p. How about now? I'll reduce the bandwidth for that. Is it working now? It's all good? All right. So if you load array element 2, it's also going to it's also going to load array element 3 from RAM. And so that's why if you go left to right through RAM like this, it's going to be much faster than if you were to like do it randomly. Like if you first printed out element 0, then element 99, then element 50, like you're still doing the same 100 operations, but if you do them in a way that's not what we call cache friendly, your program performance can actually suffer tremendously. Okay? So it's actually really important to have contiguous memory. In other words, everything next to each other as you go down the line. And if you do that, the memory subsystem will do a really good job caching everything and avoiding cache misses. Okay? Your first access is going to be a cache miss no matter what, right? Usually you start at 0, that's going to be a cache miss. But then once that's loaded and you start iterating down the line, you're going to start getting cache hit after cache hit after cache hit. Okay? So let me explain to you now why the way that I taught you to do a 2D vector is bad. Okay? So if you don't remember how to do a 2D vector, like you're going to make a board game or something like that, you want a 2D, you know, tic-tac-toe, a 3x3 kind of thing, you could do something like this. You could say, let's make a, what is chess? What is connect 4? Connect 4 is 7 columns, 6 rows. Okay, so we're going to make a vector of characters named board, and each row is a vector of characters of size 7, and we have 6 of these rows. 6 of these rows. No matching. Let's see, vector chars. Each row is a vector of chars. 7. And there's 6 of them. This is why 2D vectors make you nervous. Great. Right? Or even worse, you can do something like this. Vector of chars named vec. And each element of it is a vector of chars of size 7, and there are 6 of these. No, it's not liking that. No viable, no matching constructor. Lord. What am I doing wrong here? Switch the 2 around. There we go. There are 6 rows. Each row is a vector of characters of size 7. There we go. So that is how you make a 6-row, 7-column board. Then we can do things like, say, vector.at 2.at 4 is equal to black, something like that. And that's how you can have a 2D board for your C++ purposes. Now, why is this bad? Why this is bad is because what we're doing is we're not actually making a contiguous block of memory. Okay? So what we're doing is we're making a vector, and each one of these vectors is vector elements, element 0, element 1, element 2. Each one of these guys is itself a vector. Okay? And so it's creating, in this case, what do we have? 6 rows. It's creating 6 different vectors. And so each one of these spots in RAM is probably not next to each other. You guys see what the problem is? So it'll work. This code works fine. You can do this where you say row 2, column 4 is set to be. That's fine. But if you're going to do something like add up all the elements in a vector of integers or something like that, it will go slower. Yeah, let's actually work out the math on this. So let's say that we have 100 rows, and we have 20 columns, and the first column costs 100 cycles, and each one next to that, each one after that, costs 1 cycle, because we're going to get cache hit. And the due to the way that it does multiple issues, you actually won't even get the 4 cycle penalty. It'll essentially be free. So the very first time we load an element from a row, we're going to get a cache miss. It's going to cost us 100 cycles. And then everyone after that is 1. So if we're going to add up all 2,000 people, right? Because we have 2,000 integers, let's say. We have 2,000 integers. What is the cost going to be if we do a vector of vectors like this? Where a hit, cache hit, is 1 cycle, and a cache miss, a cache miss is 100 cycles. What's the total cost going to be? I'll pause it and let you guys do the algebra. And we're back. So we have 100 rows. So let's figure out the cost for one row. So in order to add up all 20 people in one row, the first guy is going to cost 100 cycles because that's going to be a cache miss. And then everyone thereafter is one cycle cost, right? So one costs a cycle, that one costs a cycle. And we've got a total of one guy that's a miss. We've got 19 that are hits. The miss costs us 100. The hits cost 1 each. So each row is going to cost us 119 cycles to add all the numbers up in that row. So we've got 119 cycles. We've got 100 rows. And so that is a total of 11,900 cycles. Okay. So that's how much it's going to cost us if we do it the vector of vectors approach. If we do it in a way that will minimize our cache misses, if we could avoid all of these cache misses except maybe the first one, then it would only cost us 2,000 cycles. Or if you want to include the first cache miss, it would cost us 2,100 cycles. This is sort of our optimal cost. All right. So 2,000 cycles instead of 11,000 cycles. You guys see? You guys see what I mean? Like, either way, we're going to get the same answer, right? We're going to get the same answer. We're going to add up all the numbers in the 2D vector. We're going to add up all the numbers and get the same answer. But one way is 5 times slower than the other. So do you get? Is this motivating you guys? Like, why, this topic, matters? It's a 5 times speed difference, and 5 times isn't the worst thing in the world, but it kind of is. Like going from 100 frames a second to 20 frames a second. Like, if you gave me that option, I'd be like, I think I'd rather have my game run at 100 frames a second instead of 20. That seems like a good deal to me, And it's the exact same code, you just lay it out a little bit different. You put it in memory so that you are contiguous in memory. You put all of these guys next to each other in RAM. And so what you do, instead of this thing here, is you do this. You say, I'm going to make a vector of characters named vec2 that is like that. It's a 1D vector instead of a vector of vectors. You guys understand? All 42 of these guys are going to be adjacent to each other in RAM. And so if you're going to loop over the whole thing and like add all the things together, something like that, you will do so in minimal time if you have contiguous memory like this. Okay? You guys understand? But there's a problem, right? We want to do like tic-tac-toe or something, or Connect 4 in this case. How the hell do we map from 2D to 1D and back? So if we want row 3, column 4, which guy is it out of these 42? You guys see what the topic is for today? So let's do a simple example. Let's do like a 3x2. So this is a very small board indeed. You've got 2 rows, got 3 columns, claws, 3 columns. And we need to map this to a 1D array. So we have a 2D array, and we want to map it to 1D. Okay. So the most common way we do this, if this is row 0, row 1, column 0, column 1, column 2, is the index over here is going to be 0 and 1 and 2 and 3 and 4 and 5. Okay? Just like you're reading a book. This is something called row major order. Okay? And so if the player say, hey, give me row 1, column 1, we go to that spot. Okay? It's really annoying for a player to figure out, but we're smart. We're computer science people. We can actually build a class to do this for us. So the class is going to hide the fact that we are using contiguous memory because it's super annoying for a person playing tic-tac-toe to be like, all right, index 8, set that to X. Index 4, send that. You know what I mean? Like, nobody wants to play tic-tac-toe and be like, all right, index 7, you know what I mean? It's like, nobody wants to operate in 1D, when you have a 2D board, right? So we need to do the algebra to figure out how to do this mapping, okay? So let me give you a bigger case, and let's see if we can work out the algebra together, and then we'll build a class to do it for us. So we have here 5 rows. I might have gone in over my head on this. We have 6 columns. And so this is going to map to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm going to pause the recording. And we're back. Okay. So this is all going to map. It's a 5-row, 6-column. In 2D, this is going to map to a 30-element 1D array. Okay? Or vector or whatever. Okay? So element 0, 1, so we're going to have ... all the way up to 29. It goes from 0 to 29 because there's 30 elements, right? So, yeah, the recording has started again. Yes. Okay. Let's see if we can figure out through intuition. I always like trying to get an intuition for how the math works. So Burford, let's say we are here. We're at row 1, column 2. We're at index 8 over here. ... I'm not doing this to scale. If I move one index, if I move to the east, what is the index of the person to my east? Like, let's say that you're moving a rook in chess, and you want to see if the spot to your east is open. How many indices in the 1D array do I have to move to the right to see, what's there? 1, right? So 7 is west, north, south, west, east. So if I want to move east, what is the index of my spot to the east? 9. Good. What is this index of the person to my west? 7. Yeah, so east is always 1 index to my right. West is always 1 index to my left. What about north? I'm at 8 right now, and I want to see, hey, is the spot to the north of me open, or is there a queen there or something like that? How many indices away is north? North, not south. North, yeah. 6. 6, yeah, 2. Yeah. Minus 6, right? So we're going to 2, right? So going north, we are moving 6 left. So we go 1, 2, 3, 4, 5, 6. So if we move 6 to the left, that's the same as moving 1 up. You guys see that? What about moving south? How many indices to the right do I have to move? We have 6 columns. So how many indices to the right? 1, 2, 3, 4, 5, 6. I move 6 indices to the right to move south once. Okay? So that is 6 to the right. Okay? So every time we move 6 to the right, we move south 1. Every time we move 6 to the left, we move up 1. Does that make sense? So the algebra for this is what? So if I give you a row and a column, how do I use my powers of algebra? Every time you move down a row, you go plus 6, which is the number of columns. Every time you go down a row, it's going to be row times what? Every time you go down a row, you move up 6. So it's going to be rows times 6, also known as rows. The row you're on times what? Times the number of columns. Very good. Row time, not the index, the row times the number of columns there are. We have 6 columns. So our final index is going to be equal to the row we're on times the number of columns plus the column we're on. And that is our index. So our index is equal to the row times the columns plus the column we're on. And that's in all caps because that is the size of the board. Now, if we had a 3D array, and this equation, by the way, I have had to know that equation so many times in my professional career. It's crazy. What's even crazier is that I at one point I tried memorizing it, and then I realized that I could just regenerate it every time. I could just look at the numbers here and see, okay, every time rows goes up, it's columns bigger. So that is rows. Okay. And then every time I go right one column, it goes up one. Okay, going up one column goes up one. Great. Going up one row goes up 6. Okay, great. For your image processing assignment in the past, we actually would give you a 3D array. The first plane was red. The second plane was green. And the third plane was blue. Okay. So if you go down one plane from the red to the green at the same location, you would go plus 30, right? So this guy here would be 30, 31, 32, et cetera, et cetera. So this guy would be index 35. So if you went from here to here, it would be adding 30. Why? Because you have columns times rows. And then if you went down to the same location in the blue plane, it would be 65. Okay? Because you add 30. Every time you go down a plane, you go down rows times columns, because there's row times columns, 30 people on one plane, right? Meow, kitty. The cat just came to visit me. He doesn't meow, though. He goes... I don't know if you guys can hear that. Is it coming through? So the 3D version of it is plane times the number of rows we have times the number of columns we have. This pen is driving me crazy. Every time I hit the pen, the button on it, it stops writing. Okay. Plane times rows times columns plus the row we're on times the number of columns plus the column. So given a row, a column, and a plane, this will give you the index in a one-dimensional space. So this is a 3D to 1D mapping. This one up here is 2D to 1D. This one here is 3D to 1D. Okay, and that's the algebra. And I've had to regenerate this equation any number of times in my professional career, and it's very common because holding everything in a single one-dimensional vector or array makes everything contiguous in RAM. And then everything is together, and you get that nice times whatever cache speed boost that you would lose out on otherwise. Are you guys with me on this? So Burford, you are correct. Current row times the columns plus the current column is correct. That is absolutely correct. And the best way, if you can't remember the algebra, again, just sketch it out. Just get a piece of paper and be like, okay, it's going to be row times 6, 1 times 6 plus 2 is 8. Okay, great. And just sketch it out and then just try it for a couple different locations. Because this is what you guys are going to have to do for your next homework assignment. Not Pokemon Part 2, but next Wednesday you guys will be getting a Bridges assignment. And it basically is involving figuring this out. So you're at a certain spot on the world, and you need to check the spots around you and see which one is closest to your current value and stuff like that. We'll talk about that next Wednesday right before Thanksgiving. But it involves 1D to 2D array mapping. Okay. And sounds like a cool 5 times speed increase. It is, yeah. And so, my master's degree was in high performance computing. And so you know, anytime you could squeeze performance, we would do it, you know. So let's do it. Let's do it here in code together. So that is, hopefully that's motivated you guys a little bit, right? Like understanding that you can actually get pretty, you know, pretty serious speed differences if instead of doing it this way, a vector of vectors, instead you do it this way where you have a one-dimensional array or vector. So we're going to make a board class like this. And this is going to be a class that can hold like a chessboard, Connect Four, tic-tac-toe, pinte, you know, any sort of grid. You guys understand? Checkers, right? Any sort of grid. Okay. So what kinds of things what sorts of things must always be true about a board? Finite size? What can you have a 0 by 0 board? Does that make any sense? Is a 0 by 0 board usable? Nah. So let's make a rule. Rule number 1. Or we're computer scientists. Rule number 0. Rows and columns must always be greater than or equal to 1. Okay, the smallest board we'll support is a 1 by 1 board. It's a pretty boring board, honestly. At least it makes sense. Like, you know, in the previous class, we didn't have that, and somebody's like, well, what if they make a board that's negative 50 by negative 50? It's like, yeah, good point. We should probably make a rule about that. Right? So this is in what's called the private section of your class. You actually don't need to write private because anything that's a class is private by default. I'm going to put it here just so that you guys can kind of, because this is probably for a lot of you guys the first time you've seen a private section at all. But the reason why we make something private is so that if we make a board, like let's say Connect 4 is 6 rows and 7 columns, which we'll need to make a constructor for in a second. It would be really bad if I could say Connect 4 dot rows is equal to negative 100. It'd be really bad if main could just change the size of it, and because this board would have no knowledge that its size just got set to something completely invalid. So what we do is anytime you have an invariant, anytime you have a rule, you typically hide it in the private section so that whatever dumbass programmer out in main can't break it. And oftentimes that person is you. Who's the client of your code? I am. Do you trust them? No. Right? Like, let's be real here for a second. You know, it's usually you that breaks your own code, and yeah, that's why we protect it from ourselves. Okay, so we're gonna make a constructor, and we're not gonna allow maybe we're not gonna allow a default constructor at all. So maybe we'll say board with a delete like this, and now if we try making a generic board with no size, it won't work. You have to give it a size. You have to tell it how many rows, how many columns the board has. Okay? This is a deleted default constructor. Pretty common stuff. Because if there's no, like, what's the default size? 1 by 1? That's not very useful. You know? Like, do you want it to default to something that's not useful? Default to 0, 0? That doesn't make any sense. We're not going to allow the board to change sizes later. So yeah, I would just say no. Like, you have to give us a size for this to work. The bad programmer is me, always has been. Yeah. Like I said, if you look at a lot of my code, it is me double checking me and making sure that I am not going to accidentally do something terrible to myself. And it saved me a lot of times. Okay, so we're gonna make a constructor, board integer rows and integer columns. I don't really like these names, but whatever. And we're gonna set rows is equal to rows, and we're gonna set columns is equal to columns. Now everything's capitalized here, so you'd think that this was like a constant. Usually we make constants capital. But if we tried making a constant here, we're going to have a problem. We can't set it. So there's actually a thing in C++ that allows you to set a constant. And it looks like this. I don't know if you guys like this or not. But it looks like this. And so this is a way of setting a value. And this is actually the recommended way of setting member variables. So this is going to set the constant rows equal to whatever value is passed in here. It's going to set the constant columns to whatever is passed in here. If you do it in the constructor, it's too late. If you try setting rows is equal to 4 in here, you can't set it. It's a constant. You can't change a constant. So the only way you can set the value of a row of rows or columns, which are constants, is by doing this thing. And it's a colon, which looks weird. It's a colon, and then it's a list of a variable, a member variable, and then the value you're giving it. So if we wanted to have a default constructor, we could do something like this: rows 10, columns 10, and then now we can have a default constructor that'll default to a 10 by 10 board. Okay, that's how you can do this using colon, the name of the member variable, and the value that it is initialized to by default. Okay. Another way you can do it is just by just setting it here. This is modern C++. The old way of C++ is using the colon thing, which, let's be honest, is just not as pretty a syntax. It's just setting it here. Okay. But yeah, let's do this. And the constructor itself, what if, and we can't do this because it's private. Okay? We can't change it. What if the user tried doing something like this? Let's make a board that has -6 rows and -7 columns. What rule did we break? Autocorrect to be positive? Now I'm surprised people. What if it's 0, 0? We should die. All right, that's just the only acceptable answer here. In a homework assignment, you die. In a professional environment, you'd probably throw an exception or something like that. Okay, so you would say if rows is less than or equal to 0, or lagging, okay, or columns is less than or equal to 0, die. Okay, double check it. We can verify that this rule is never violated. You understand? When we have an invariant must always be true. And so that's why we put things into the private section. We put things into the private section whenever you have something that must always be true. By putting in the private section, this allows us to verify and double check and make sure that anytime we work with rows, columns, whatever, that it can't change, it can't be negative, it can't be 0. Okay. We should die. Yeah, I think there's a sticker for that. Yeah, there it is. Let's see if there's a way I can get it on the screen over here. Won't open in a browser. Yeah, anyway. Okay, so then we are going to use this pointer here to hold a 1D array. And so what we're going to do is we're going to say R is equal to new integer rows times columns. And we're going to initialize it all to 0. Okay. And so what this is going to do is, well, we probably need an invariant for this, right? So what rule should we have about our R pointer here? Screenshot open in Paint or whatever. Just for the people at home, I guess. Sure. Snipping tool. There you go. Exciting. All right. So what is the rule that we should have for R here? And technically we don't need to set it to null pointer because we're about to initialize it. Because R probably should never be null, right? Like R should always be pointing to a 2D double quotes array of size rows times columns. Kitty. Hi. Okay. Do you understand? So at no point in our class will array ever be pointing at a null pointer, at corrupted memory, at anything. It's always going to be pointing to a chunk of memory that is exactly rows times columns in size. You guys understand? And this is why it has to be in the private section as well. If we put this in the public section, we can no longer enforce that. We would be able to say connect for.r is equal to new int, square bracket 1000 or something like that, right? We could break it, or even worse, we could set it equal to size 1, right? And we have no control over enforcing this rule anymore. Okay, so anything like that, where any time where you have a rule that has to be enforced, that thing has to go in the private section. Are you guys with me? That's why the private section exists. It exists so that you can enforce a rule that array is never null, array is never pointed at bad memory, rows is never negative, columns is never 0. Anytime you have rules like that must always be true, you put them in the private section. Okay. And there we go. So now we need some ability to read the value of the board. We need the ability to set the value of the board. Let's say the number that we're setting here is the player that owns the piece, like we're doing checkers or something. So that's how we can throw out bad inputs in the class as a Pokemon assignment. There should not be any bad input in Pokemon Part 1. So if you're getting like an exception or something like that. Like for the moves, right? For the moves, yeah. Oh, for the extra megas, yeah. It's not bad input technically. It's just you're getting a duplicate entry. And so what I do is I read a Pokemon, and then if the Pokemon has the same Poké index as the previous one, I just discard it. I don't push it back into the vector. It's not like I'm calling die, because it's not like a terminal, problem. It's just the rule is you can only have one Pokemon of each Pokédex number. And so once you've read 50 Diglett, if you read Mega Diglett at 50 also, you just throw it away. We're just only accepting the OG original Diglett, not a lowland Diglett or whatever. But yeah, if you do have an erroneous scenario, then throw an exception, or there's different ways of handling errors, and that's a whole lecture we're going to have next week, actually. Now, okay, so we need the ability. We could do something like this. We could say get rows. That seems useful. Return rows. Right. It's kind of like in a vector, how you have like a size, kind of thing. In fact, we can even do that. Let's say size const return rows times columns. Just like how many elements we have, right? Because let's fix this down here, right? Like, because we know down in main we've got 42 elements, but we might forget, or we might pass this thing to a to like a function or something. We have a memory leak right now, don't we? Anyone else notice that? We're allocating memory. We are not deallocating memory. Sorry to compile this code right now. Main.cc. With address sanitizer on, let's bring in sanitize equals address. Bring in asan and run it. You will see we have a memory leak. Okay. So we do not have a delete. So this is a learning point called a destructor. So a destructor is like a constructor, except it has a tilde in front of its name. Okay, so let's list our learning points here. Learning point number 1, 2D to 1D mapping. That was that whole thing earlier. Learning point number 2, anytime you have an invariant that must be true, you should protect that thing inside the private section. Learning point numero 3, destructors should free resources allocated in the constructor. And this is something called resource acquisition is initialization, which is a dumb acronym. It doesn't make any sense. It's like the BSS. What does it stand for? Nobody knows. Nobody cares. I mean, we know, but like, it doesn't matter. So RAII, like Ayanami RAII, right? Except spelled differently. RAII, Raymond, means anything you allocate in the constructor should be freed in the destructor. And what that makes it really nice is, finish this, delete R. Down here in main, we don't have to do any news. No news is good news, right? Like I can make a board here, and I can make it connect, I don't know, 5 board that's 60 by 70. And look, no memory leaks, right? When I make the variable in main, it allocates the memory. And when the variable goes away, the destructor gets called, and it frees the memory. And I don't leak memory. I don't have any news. I don't have any news. No news is good news. And in fact, if I was coding this today, I probably wouldn't even have the new there. I'd probably use a vector or something like that. But this is for point of education. Yeah. So show number, set number. There it is. Okay. So what line? Where does the destructor get called for connect 4? Anyone know? On what line? It's a very special number in computer science. On what line does the destructor implicitly get called? I don't ever call the destructor by hand. It gets called automatically when the variable goes out of scope. What line? $32 is the line of the destructor, but it gets called on line 42. Okay. So on line 42, on that closed curly brace, that's where connect 4 gets its destructor called, connect 5 gets its destructor called, and all that memory gets freed up. Okay. So when the variable is made, here is where it allocates the memory. Here on line 42 is where it frees up the memory. And so you can just use these board objects as much as you want. They'll allocate memory, they'll deallocate memory. It's just nice from the end point of view of the user. Okay. Now, we need to come to the meat of it, which is the mapping. Okay, so we're going to have an int get, can then take in a row and a column. And we want to return the value at that row, at that column. Okay, so we want to return our square bracket something. Anyone remember the algebra that goes in here? Given a row, given a column, given a row, given a column, we return from a 1D array, we're doing a 2D to 1D mapping here, we return the index of that spot. If we pass in row 1, column 2, on an array of this size, we return array square bracket 8. Okay. It is toe row. It is row times columns plus column. This is the equation, 2D to 1D mapping. And the reason why we do this, again, is so that everything is contiguous memory, because the most common way we have of iterating across a 2D array is left to right, top to bottom, and that's how it's laid out. Okay. Now, we also need to set our things, so we can have void set int row, int column, int value, and we can say array square bracket row times column plus column is equal to value. And so we can get the value of our board. We can set a value on the board. The only other thing we'd want to do probably is like print the board, something like that. And we can have a void print function. And it should also be class probably. So if you guys did these Xi books, you know about something called a copy constructor. I'm going to delete it so that we cannot make a copy of this board. Boards should only be passed by reference. If we ever pass a board by value, we're doing something wrong, undoubtedly. And so I'm going to delete the copy constructor. And then if I have a function, like if I was going to do a global print function or something like that, and I tried doing board B like that, cout b dot get 0. Then this will not work. You cannot pass it by value, okay? Because it's a big thing, right? We could have 1,000 by 1,000. We do not want to be duplicating all of this data by accident, right? So this thing can be passed by reference. That's fine. No problem. You can pass it by const reference, even better, but we can't pass it by value. I will disallow this thing to be passed by value, which is a good thing. You also can't duplicate it at all. Okay, so that's, for those of you that have done the Xi books and know about copy constructors, I'm actually just deleting it. It's probably the correct thing to do. Here. Okay, so we want a print function. So we want to print all the elements in the board. So it's a 2D thing. So we say print I equals 0, I is less than rows, I plus plus. We always do rows first and columns second. J, J, J. And we will cout. Now I could do the math again, right? I could cout R square bracket I times columns plus J. I could do this, I could, but why? When I could just call get. I've already done the math once. I don't ever have to do this math again. You guys understand? So I'm just going to output the value at row I, column J. Then at the end of the row, I am going to do a little inline, and there we go. So if we say connect for dot print, all zeros. Let's set some pieces on it. So we'll say connect for dot set. So on row 5, column 0 on the bottom left corner of the screen, I'm going to set it to player 1. And on, player 1. And on the spot next to it, I will set it to player 2. And then on top of that spot at row 1, I'll have player 1 move on top of it. Yeah, okay. And then we'll print it. And there you go. You can see player 1 moved there, player 2 moved to the right, player 1 moved on top. You guys see that? Zeros indicate blank spots in Connect 4. 1 indicates player 1 is there, 2 indicates player 2 is there. Now, we got some bugs in this code. Anyone see any? What's the first thing you should always do whenever you have a function call? You have to turn on your paranoia a little bit. It's that dumb idiot that's using your code to do something bad. So what are we missing? We got 2 functions that are really bad. What are we missing? What checks are we missing? Could you set player 2 to a place where player 1 already is? Yeah, but is that the responsibility of the board class? Like, should the board class know anything about the rules of Connect 4? Or should that be like main? Because main is going to be inputting like what column you want to put it in, finding the first open spot. Like, I don't think the board technically needs to worry about that because this is a generic board that could work for chess or tic-tac-toe or whatever, right? And in chess, like, you can, move on top of somebody's square. So you could have a separate Connect 4 class. You could, but for this board class, there's 2 very serious problems. I could get my board class to crash right now. Sec fault. What would that look like without address sanitizer? Look like that. A little less useful. Address sanitizer tells you, hey, line 58, calling this function, line 42, you done goofed, right? If you don't have address sanitizer on, you just get seg fault, core dumped. And that's not very useful. It's like, cool, where? Thank you, C++, very cool, but where did I crash? If you have address sanitizer turned on, it'll tell you. It's like, on this line, you crashed. You made a big oopsie. You made an oopsie daisy. Okay. So, which functions do I need to add some checks? Maybe we should have another rule. I don't know. What do you guys think? Rule number 2, never allow access outside 0 to rows -1 and 0 to columns -1, something like that. That makes sense? Because if you have 10 rows, it goes from 0 to 9. Something like that, maybe. Okay. So we got a rule now. That's cool. So if this was public, we could just access it, right? And go right out of bounds on it. So fortunately, though, we have these class member functions here, methods here. So what should I put here? If what? Die. What should I put here? What values are invalid? Obviously, 4 million doesn't work. What other values don't work? So, if row is greater than or equal to rows, or column is greater or equal to columns, obviously we should die, right? Sure, but what other values are bad? You got to think like a hacker man, right? Which possible values should we look out for and reject? Anything less than 0 is correct. Yeah. Exactly. And so if row is less than 0, or row is greater than or equal to rows, or column is less than 0, or column is greater than or equal to rows, this pattern here you will see everywhere. Anytime you have a 2D rectangle You check to see, am I off the west edge of the rectangle? Am I off the east edge of the rectangle? Am I off the north side of the rectangle? Am I off the south side of the rectangle? Do you guys understand? You got 4 corners, you got 4 edges to a rectangle. So every time you do anything with a rectangle, the first thing you do is check to see, am I actually in a rectangle? You know, and if I'm not, then in this case, die. But in other cases, you know, you just return or, you know, whatever. Players, you're lost. So Burford, do you understand why this was crashing? Why would it crash if we try accessing memory, you know, a gigabyte past the end of our array? So our heap, right? You guys remember the memory map. What other things could crash without a bounce check? Just what kinds of things should we check for, you know? And so what's happening here is we are going outside of the boundary, right? The heap has a fixed size, and we are accessing something beyond the segment boundary. So we access something up here. We were trying to access something in the heap. We access something up here. And that's why we got what's called a segmentation violation, okay? That's why we get a seg fault, okay? Segmentation fault means you've got a chunk of RAM in your segment, the stack, the heap, whatever, and you went outside of it. If you step outside of it, the operating system will detect it, you done goof, and kill your program. Now, if you have address sanitizer turned on, it's not the operating system detecting this, it's your own program, because it actually builds instrumentation into your program that every time you do a memory access, it checks to see if that memory access is within the bounds that are valid for your arrays. And so we're getting a segmentation violation right here. And it tells you this line called this line. And then you go, huh, let's look at this. Vim main.cc line 60. Okay. That seems suspicious to me. But why is set not catching it? Like, we don't have a boundary check there. Every time you have an array, you need to do a boundary check, right? At some point. Otherwise, you're just hoping and praying that the code's not going to crash, which is really bad. And in fact, this should actually just copy paste just fine. Okay. So if we try setting something out of bounds, too far left, too far right, too far up, too far down, crash. And Burford suggested that we don't allow players that are like only player 1 and player 2 could be set, but what if it's a 4-player game? I don't know. Because again, we're making a generic board, right? Like this is just a 2D grid, you know, for like tic-tac-toe or Battleship maybe. I don't know. Like there's no specific like rules for like what numbers it could hold or whatever, you know what I mean? Imagine if it's in that's true. That is very true. Yes. Yeah, I like the cut of your jib. So if we do this now, right, it's gonna just we're handling it now. Good. All right. But let's go back to here and let's set 100 here. Now the formatting is all screwed up. All right. So maybe I don't know. Maybe we should just limit it to the numbers from 0 to 9. Does that seem reasonable? Because if we allow something like this, then the formatting gets screwed up. It seems reasonable. Maybe another way we could do this is like do something like that, where we like tab delimit it, and then the formatting doesn't get screwed up. You know what I mean? At least until you have like really big numbers, right? Like if we put like I don't know 100,000 in here, let's try that. Nope, still works. Maybe 3 digits more though. It'll break 100,000, million, 10 million, 100 million, something like that. Yeah, eventually it'll break, right? But I don't know. I'm not sure I care enough about it to, you know what I mean? Because like, I mean, should you kill the program if the user puts a 500,000 there? I don't know. Probably not. You know, like if I'm just making a generic board class, I don't want to like dictate to the user, like, you know, you can't use a number, you know, bigger than, you know, 1,000,000 or something. Might have to redo the print function. I don't know. It's not a fundamental error. Yeah, exactly. It's a cosmetic error. And, you know, back in the day, I probably would have cared a lot more. I probably would have set up some sort of like, I would have scanned all the values and saw which one had the most digits in it, and then like set the column width to be that big. And nowadays, I just take the Bethesda approach. You know what? If the bush goes through the wall, the bush goes through the wall. Who cares? You know? If the NPC walks into a chair, you know, and kicks the chair over, who cares? The charm of it. Yeah. So. Don't sweat the small stuff. Yeah. But for things like seg faults, like that's not the small stuff. You know what I mean? So for things that will absolutely toast your program, you know, cause it to crash, that's absolutely something that I worry about. Like I do not write code that will crash. It's kind of a big statement. Yeah. Like it's just not something I do. Like it's incredibly rare for me to write actually a program when I'm actually coding for real, or like anything the user can do can crash the program. Like I always double check everything the user does, and I make sure, you know, I've got my class invariants, and I do bounds checking on everything, and just the way that I code lends itself to just like I don't seg fault these days. Like it's been 7 years, I think, since I seg faulted like in my own code. And that seg fault was me introducing a bug into my code because I was writing a program that would check for bugs in programs, and so I added a bug to the program that checked for bugs, and then ran the program on the code, and it didn't find it, and then I forgot I put it in there, and then it was seg faulting, and then I got to spend like 5 hours trying to figure out why my code was crashing until I finally found that it was me that had added it, and then forgot about it. Yeah, that was a great moment when you found the culprit. You know, it was a mean bug too. Like I hit it pretty well. Shouldn't have forgotten about it, but I did. So I was coding like at 3 o'clock in the morning, and I was like, I'll get back to this later. Why is it? You know, the next day I'm like, why is my code crashing? You know? 2,100 days since the last incident. Yeah. So it's like if you want to crash, you can, you know, but like the way that I code, the way that I go about doing things with bounds checking and enforcing invariants and things like that, I really just don't seg fault anymore. It's just not a, you know, it's just not a concern, you know, and that's something that a lot of people that hate on C++ have trouble like grasping, which is that like you don't need to write code anymore that has pointers and you know, news and deletes and things like that. Like I generally speaking use what's called the rule of zero, which means my code has zero of any of that stuff. No news, no deletes, nothing. And it works nice. It works really nicely. And you just don't, just all those problems you have with like dangling pointers and invalid references and double deletes and memory leaks and all that stuff. It's just, yeah. If you code using modern C++ styles, AC2 178-ish. There's board games this Friday. If you guys, sorry, I just got a message from a student. When is the board games? So yeah, this Friday, board game club meeting. You guys want to be there? Also, there is there's a bunch of other workshops coming up, so check the workshops channel for that. And that's basically where we're at for today. So do you guys understand this code? Is there anything I have up on the screen here that is not clear to you? A print function that, again, I could probably revise that and make it a little bit more intelligent, but I don't care. You know, like learning what to care about and learning what not to care about is actually a big part of becoming an experienced programmer, right? Like I would stress over like so many things as a new programmer. Like, oh my gosh, my gun is going through the wall in the video game. And how do I, I'm going to have to dynamically have the gun retreat. And then I look at professional games. I'm like, oh, they just let the gun go through. Or constructors and destructors, sure. So when you make a new variable of the board type, so we'll say board of directors. This is a 1000 by 1000 board. This calls the constructor implicitly. Okay, so it secretly will call the constructor up here. Scroll up a little bit. Did you like that one? I didn't like it. It wasn't my best moment. So this constructor here, this constructor gets called when a new board is made. And inside of this constructor, we're doing a little bit of error checking. We're making sure the size of it's not negative, which would be really bad. Feasibly, we should probably put a size limit on the top end of it as well. Because, if we passed them like 4 million by 4 million, we'd run out of RAM and crash. So, maybe we cap it. I don't know. So when you make a new board like this, we're making the board of directors here, which is a 1000. This is a big board game, right? Then it's going to call that constructor. It's going to make a array of size 1 million. And then down here at the very end, when the thing goes away, this line here calls the destructor on connect for and on of directors. So we've got two different boards. We got one whose name is connect for, one whose name is of directors. When you end the scope of the scope that they're in, a scope is something like this. If you did this, let's do this. Okay. You can actually just make a scope like this if you want. So cool. All right. Garza, what line number does the destructor of directors get called on now? So when does of directors go away? When does that destructor, which frees up the memory? You don't need a destructor if you're not doing anything with allocated resources. Like if your constructor doesn't do anything useful, but just like initializing some variables, you don't need a destructor. Who cares? You use destructors when you are doing something like opening a file in the constructor, then you have the destructor close the file. If you have the constructor open a network connection, you have the destructor close the network connection. So anytime you have this kind of yin-yang balance kind of thing where something in the constructor has to be paired with something in the destructor, you need a destructor. But if all your constructor does is just like set everything to 0, you don't need a destructor at all. And that's usually how I code. I usually write my code where I don't have any copy constructors, I don't have any destructors, I don't have a move constructor, I don't have a move cop. Like, it's called the rule of 0. And the rule of 0 means just you don't do any of that sort of memory allocation or deallocation thing anymore at all. When the copy constructor line just stop you from creating a constructor with a const reference parameter. Now, this is a special thing. So if you haven't read the Xi books on it, the copy constructor is called whenever you... so yeah, it looks like it's a constructor taking another board as a constructor. Like if you're doing something like this, like board of directors, right? It looks like this, right? And it's been deleted. You can't do it. But the copy constructor is actually called when you do call by value parameters. So void Bob board B call by value calls the copy constructor. And so if you were to call Bob directors, that's not allowed. And that's why I deleted it. It's because I should never pass a board by value, because now you're duplicating it. And when you have you could have 1,000 by 1,000 board, you don't want to duplicate it by accident. Like if I wanted to actually go to the effort of duplicating the board, I'm going to need to do that quite explicitly. A lot of students will just kind of forget the ampersand, right? But you put the ampersand there, it's fine. It's called by reference now. It doesn't duplicate it. Call by value, though, would be really bad from a performance standpoint. There's also another issue, which is something you'll learn more about in CSI 41. If you duplicate a pointer, now both pointers are pointing to the same chunk of memory. And when the first one goes away, it kills that memory. And the second one's now a dangling pointer, which is why you have to have a copy constructor anytime you have a pointer. But I just deleted it. It's fine. Modern problems require modern solutions. Yep. And also the copy constructor would work like this. Board goo is equal to of directors. That's technically the assignment operator, but this will actually call the copy constructor, which is, again, forbidden. We have not allowed any copies of our board to be made. So if I try duplicating it like this, it is forbidden. If I try duplicating it like this, it is forbidden. If I try duplicating it board of directors, if I try duplicating it like this, it's forbidden. All of these are forbidden. I do not allow making a duplicate of my board class. Okay. It prevents any form of copying, kind of. I mean, I could make a new board of the same size, and then write a for loop that copies all the values over or whatever. But just any of the built-in C++ ways of copying something are now forbidden because of this line right here. So this is, again, more of a CSI 41 topic, which is why I've been kind of not going into a lot of detail on it. But yeah, I deleted the copy constructor. Now you cannot copy any of the boards, easily. So all these different ways you could copy it, none of them work, which is good. Okay, so where were we? So Garza never answered. So let's go back to Burford. What line of code is connect for being deleted on? Where is the destructor being called? Oh, you weren't sure where the question was. Okay, Garza, you're back. Okay. So Garza, which line of code is the destructor for connect for being called on? And Burford, you can answer which line of code of directors is being destroyed on. Where is that destructor being called? Good. Burford, that is correct. Very nice. Garza, what line of code is the connect for destructor being called on? We can even add some cout statements, maybe. So I don't mess with the 67. Just so I don't mess with the line numbers, right? And then in the destructor, cout destructor called. I didn't mess with any of the line numbers. Great. Okay. So Garza on line 66. 66, you think the board of directors goes away? Let's find out. And take a look at it again. I'm sorry, I added these cout statements. And I've added a print on the destructor. So we'll see line 67 runs. Line 68 runs. Destructor. Line 69 runs. Okay. So Garza, it will run on... Well, let's find out. Okay. So you can see here line 67 runs. Line 68 runs. Then the destructor is called on this guy right here. So connect 4 is destroyed on line 68. That closed curly boy is the tombstone signifying the death of the Connect 4 board. So when you get to the end of the scope, the ear within, it automatically calls the destructor. Okay? The destructor is automatically called when a variable goes out of scope. Okay? And then, yeah, a scope is a open close parentheses, right? And then the so connect 4 dies here, and of directors dies here, and I could put other stuff in there. Hi, how are you? Yep. So when something goes out of scope, that's when the destructor is called. Yep. So it's going to print destructor called. Hi, how are you? Destructor called. Makes sense. And like I said, normally, like when I write code these days, I don't have destructors, I don't have copy constructors, I don't use any of that stuff because I follow the rule of 0. So, no news is good news. All right, that's our class for today. Make sure you get Pokemon Part 1 done by Friday, and then I will see you guys on the flip side. Next week, we got a half week because it's Thanksgiving, but we will have class on Monday and Wednesday both. No class next Friday. And make sure you sign up for the workshop opportunity. So pop on over to the workshop channel in a second, and I will post a cool opportunity for you guys to sign up for. All right, see you guys. Peace.